Hello everyone, thank you all for joining us today, and I'm very excited to share with you our research on 3D visual grounding, a rapidly evolving field with significant implications for various cutting-edge applications like autonomous robotics and metaverse. First, let's establish what we mean by 3D visual grounding. Essentially, 3D visual grounding is a task of identifying and localizing objects within a 3D space based on a series of text descriptions. Imagine we have a 3D scan of a room and a description like, "It is a keyboard close to the door," as shown in this figure. And the goal is to accurately locate the keyboard within the 3D environment. Traditionally, solving this problem has required supervised learning methods. These approaches rely heavily on extensive annotations and predefined vocabularies. While effective, they are incredibly resource-intensive and not very flexible when it comes to new, unseen categories or open vocabulary scenarios. To address these limitations, our team has proposed a new visual programming approach for zero-shot open vocabulary 3D visual grounding. This approach leverages the capabilities of large language models, or LLM for short, to perform 3D visual grounding without the need for extensive annotations. One of the exciting aspects of our approach is the dialogue-based interaction with LLM. Let me explain this with an example provided in our research. The process begins with a unique dialogue that engages with the LLM to establish a foundational understanding of the 3D scene and the task at hand. Imagine we have a 3D scan of a room and the text description. It is a keyboard close to the door. The dialogue-based method will start by describing the location and size of all objects in the scene to the LLM. The LLM is then prompted to distinguish the object of interest through an interactive dialogue. For instance, when the LLM gets object information, it can extract the potential objects relevant to the prompt, that is, the keyboards and the anchor store, and successfully identify the target keyboard by computing their distances with the door. Despite the simplicity of this approach, it faces challenges due to the inherent stochasticities and control limitations of LLM. This makes it hard to capture view-dependent queries and decipher spatial relations in 3D space. To address this issue, we further developed a new approach based on visual programming. Our method proceeds through three main steps. First, we generate a 3D visual program using the LLM. This program is essentially a structured representation that includes modules like view-independent, view-dependent, and functional modules. These modules work collaboratively to perform complex reasoning and inference within the 3D space. Let me dive deeper into these modules. The view-independent modules process elements that do not change with the observer's viewpoint. For example, the size or the type of an object remains constant regardless of where you stand in the room. And the view-dependent modules handle elements that change with the observer's viewpoint, such as the relative position of objects. For instance, from one angle, a keyboard might appear to be in front of a monitor, but from another angle, it might appear to be beside it. And the functional modules are designed to execute specific tasks, such as filtering objects by their attributes or computing spatial relationships. And another critical innovation in our research is the language-object correlation module. This module is crucial for extending the capabilities of existing 3D object detectors to handle open vocabulary scenarios. It operates by merging the geometric discernment of 3D point clouds with the fine-grained appearance details from 2D images. For example, if the text description mentions a red chair, these modules help correlate the text with both the 3D shape and the 2D color information to accurately localize the red chair in the 3D space. The correlation module works through two main steps. First, it extracts potential object candidates from the 3D scene using conventional 3D object detectors. Then it refines these candidates by integrating text descriptions with visual features from 2D images. This dual approach ensures a more comprehensive understanding and accurate localization of objects, even in complex environments. And the right figures show that with this module, our approach achieves better open vocabulary visual grounding performance than supervised approaches because their vocabulary is fixed. To validate the performance of our approach, we conduct experiments on two popular datasets, that is, ScanRefer and NAS3D. Unlike previous studies that evaluate only a few samples, we consider the entire validation set, and the results are promising, showing that our zero-shot approach can outperform the state-of-the-art supervised baselines. This shows just how powerful our approach is at hand open vocabulary scenarios without extensive annotations. We also conduct several ablation studies on our methods, and the tables 5 to 8 provide insight into the performance of different modules of our methods. We find that view-dependent relations like left and right, and view-independent relations like closed are crucial for the system performance. Moreover, the compatibilities of our methods with various 2D and 3D perception models underscores its robustness and adaptabilities. Last, we give some visualization results of different methods on 3D visual grounding. And it is clear that our visual programming approach can accurately localize objects based on text descriptions. In summary, our research presents a new approach to 3D visual grounding, combining the strengths of zero-shot learning and large language models. This innovation not only reduces the need for extensive annotations, but also enhances the flexibilities of 3D visual grounding in real-world scenarios. So that's all of our presentations, and thank you for your attention. And I look forward to your questions and an engaging discussion on this exciting advancement in 3D visual grounding. Thank you.